Good morning, everybody. We've got exactly 9 o'clock, and we have to accept that some people who are still enjoying breakfast will come during the lecture. Anyway, it's my great pleasure to introduce the Professor Dr. Zainuddin Abdul Manan, who have got very distinguished career. He studied in the US, and after the universities which we shared together, UMIS, the University of Manchester Institute of Science and Technology, University of Edinburgh, he received BSc, MSc, and PhD by my humble judgment at one of the best educational institutions in the UK. He's been, after the short spell in industry, founding Prospect Research Center. He's been a full professor. He's been the dean of the Faculty of the Chemical Engineering. He received numerous awards and prizes. I would like to mention just a few, because otherwise it would be my lecture and not his. Pannonia Award from the University of Pannonia. He's been invited for annual lecture to deliver at Imperial College of Science and Technology in London. And, okay, microphone woke up as well. And many other different places. He published over 150 papers. Some of them become the classical in the field of energy and especially water saving. So, well, he has got also prizes for the best young researcher in his country, best researcher, and others. So, because I already spent 3 minutes of your time, Zain, it's my great pleasure again, and please take the floor and deliver your plenary lecture.
Thank you very much, Yiji Clemens, for the kind introduction. It gives me great pleasure to be standing here today to share with you some experiences that we have, as well as some of the work that we have done together with many people who has contributed to the work over the years on how together we can achieve water sustainability from our perspective via holistic water minimization. I hate to shock everybody in the morning with a statistic like this, to wake everybody up. But this is a fact that has been recorded by the World Economic Forum on Global Risk report in 2014, very recently, that water shortage is classified as one of the biggest or highest global risks there is. You may be wondering, why is it the case? Why is it not energy? Why is it not other things compared to water? Let's see, let's analyze water usage in a bit more detail. Water usage requires energy usage, as we know. Water usage requires sometimes significant amount of energy use. Okay, there is a hyperlink to that. Let's try to analyze why water and energy is very closely related. From this water value chain that many of us are quite familiar with. Water comes from sources, water sources, and then is being conveyed through water treatment center, and then distributed to consumers. After that, it's being treated as wastewater. Wastewater is being treated after use in treatment of sewage, and then discharged according to standards that's required by every country before water sources is generated again. So you will see that every stage in its water utilization requires none other than energy. Every stage requires none other than energy. It means that other than you using water and pay for water, we also have to pay for energy throughout the value chain of water. Okay? So I call it as W3E nexus. Yeah, W3E. What is W3E nexus? W3E nexus means that water is closely linked to energy consumption and linked to environmental consumption, and then also linked to economics or linked to costs, because water requires energy and you pay for the energy cost throughout the value chain of water. Water, you pay for the raw water bill itself, and you pay for the chemicals to treat the water, as well as you have capital costs for water. The bigger usage of water, the more you have impact on the W3Es. Water, energy, environmental, and economics. So far, people have, known it, that there is close nexus between water and economics, but they have not put it in this form. Let's go back to the figure that I have before. Yeah, so we know that water usage is closely linked to energy usage, yeah? And water usage is also closely linked. Because of we using water, we tend to pollute. Yeah, we tend to pollute to a certain extent, yeah, to varying degrees we will pollute. We also will pollute not just water, but we also pollute the environment, we generate gaseous emissions. Why? Because as you use energy, you also emit, yeah, gaseous. And as I mentioned to you, water is also the cause of global warming, climate change. Yeah? Why? Because we pollute water as well as we pollute the environment, we generate gaseous pollutants. So this is the environment nexus. And on top of that, we also know these are the costs of water shortage. All these, the three nexus, are the costs of water shortage. Why? Because energy usage, on the other hand, requires significant amount of water. When we produce steam, we need water. When we produce renewable, we also need water for cooling, for example. So energy usage is a big contributor to water shortage. So does, for example, pollution is a big contributor to water shortage, because when you pollute the environment, we also have less quality water. So in the end, that nexus is actually reversible, typically. There is also the link between water shortage as well as the climate change. Recently in Malaysia in particular, we have a very big flood. You may have caught the news in the news, a very big flood. Because of the flood, all the people affected by the flood has problem having access to quality water. And that caused water shortage. Even flood disaster linked to the climate change caused water shortage. And you can be assured drought is also one problem of the climate change that causes water shortage. What other things that cause water shortage is actually what we know already. Population increase, demand for water has increased over the years, and basically industry, including agriculture may be the highest demander for water. And in the end, all these contribute to a major risk in the world, which is major economic risk. The United Nations Environmental Program has estimated about 63% of all risks are associated to water. That's why water is the biggest global risk, to answer the first shocking news. Yeah? So that's the thing that what I call as W3E nexus. The last E is the economics nexus. This is a big risk, major risk. So by 2030, it is estimated because of the water shortage, the world is projected to face a 40% global water deficit under the business as usual climate scenario. This is basically reported very recently in 2015. Okay? So the question is, what are we going to do here? We will be sharing you some experiences of what we have been doing. You may share your experiences because ours is just one of the many experiences that people have done. And this is the topic that I'm going to talk about today. The W3E Nexus, achieving water sustainability through what I would like to differentiate between piecemeal and holistic strategy, the system approach. I will go through this quickly. I do not think I have time to go through the details, but I need to share these things. And if time permits, I will share a video about 2 minutes of what we have done in UTM, for example, to raise awareness to students on water sustainability. Some take-home messages after that. Okay, back to the water value chain. We can divide the water value chain into two sides. One is the supply side, the other one is the demand side. Yeah? In particular, we also remember that we have 3 E's to worry about. Yeah? W3 is water, energy, environmental, and economics to worry about. When we find solution, when we propose solutions, it better be that we subject every solution to this nexus of W3E. Yeah? So in particular, I would like to draw our attention to the demand side of the problem and less on the supply side of the problem, because this is beyond the domain of what I'm doing. Maybe many of you are working in this area of policy making, supply side, because this is typically the side of the authority, policymakers, government, yeah? And many other people are more expert on this. I'm not qualified to talk about this area, and basically we will cover more on the demand side of the problem, okay, which is the user side. And the user can take the form of industry, public and commercial facilities, as well as domestic and individual. This includes agriculture, when we talk about industry. We can change behavior, which is basically related to the supply side, as well as the demand side, where government can enact policy, give motivation and regulations to encourage people to make wise use of water. And what I'm going to focus more about is to engineer sustainable water systems. So these are some of the typical solutions that we can highlight. For example, people talk a lot about to treat water, treat and treat and treat water. For us, this is very good, but this is the end of pipe treatment. Yeah? So do we build bigger wastewater treatment plants? Or do we treat the water ourselves, yeah, wastewater, such that in some countries they do that. The wastewater is being treated, even the black water is being treated until they can be potable water and drinked. You can drink from them. Yeah? Or do we do rainwater harvesting? Some people propose. Some people are very passionate about rainwater harvesting for good reason, for great reasons to do so. There are very good solutions, and other people suggest water efficient facilities. These are all excellent solutions, but the only problem is that we want to see how do we put these things together, and are there things that we can do that is connected to one another? Yeah? So what are the greenest and holistic ways to basically achieve water sustainability? First, yeah, and foremost, can we think about not to use water in the first place? And secondly, if we cannot avoid using water, in many cases that is not avoidable to use water, can we use water less? And finally, yeah, there are many water using options, and some of the examples I've already mentioned to you. Can we take the best mix of these options and not just pick one at a time as convenient, because the supplier suggests you to do this and that? What are the holistic way to put all these things together? These are, to us, what we want to propose. Yeah? And maybe you can counter-suggest on better ideas to be greener and holistic way to reduce water. But at all times, try to apply the W3E. For example, if, for example, people suggest to us to use, reuse, and recycle, does it conflict with the W3E scenario? Do you use significant amount of energy to use, reuse, and recycle, for example? Does it pollute the environment? And what about the economics? That W3E has always come into the picture. So This is the topic I try to focus back, engineering water sustainability. Now is engineering water sustainability. We focus on the engineering solutions of the water side. This is what we have done, and this is basically, we have done with a company some years ago, and those people, the engineers here, are from the company, the senior engineers from the company who participated in this particular project in Mimos Semiconductor in Malaysia. And this is some of the things that we have documented, none other than the chairperson over there is the basically editor of the book and the first author of the book that we have done together, and we contributed towards the chapters on water minimization. Let's see the water management hierarchy which we have introduced and deliberated as well as explained in many of the publications that we have shown. First, let us try to reuse water, as much as possible. When you have a water source, for example, you have them anyway, there is no sense in eliminating the water source first, even though eliminating seems to be a good option, but there is no sense in doing that because what you have created cannot be destroyed. If you have created the waste of water, the only thing, the most logical thing to do is try to recycle the water. You cannot, well, there are ways to do it, but it's more difficult, and W3E, basically if you're subject to W3E, it may be more difficult. And then the next level of the hierarchy, once you have exhausted the options for reusing the source that is already available, then you try to do the source and demand manipulation. Try to manipulate the source, eliminate the source, for example, or eliminate the demand, reduce the source or reduce the demand once you have done the reuse. And then try to think about outsourcing the water, means trying to get river water, snow water, or whatever water that is available in the environment that can be used directly. And then what you have in terms of sources of water, try to regenerate and reuse. And then finally, wastewater treatment is good, but that is the last option or the end of pipe, before we discharge to the environment. So those are the things that we propose for us to do. What has been done so far? I'm going to get more technical, allow me to do so here, but not for long. Summary of the state of the art on water minimization, on engineering water sustainability, and I'm going to focus my attention on water network design and optimization. What has been done so far in water minimization research is basically revolve around, there are so many authors such that I will take pages and pages to highlight the authors, not meaning not to highlight them, but the areas only, network design, minimum water targeting, and focusing largely on 3 R's, reuse, recycle, and regenerate. And a very small portion, or almost none, except what is being highlighted here, focuses on the hierarchy, on elimination, source and demand manipulation, but reuse, regenerate, and recycle, we have been aware there's significant amount of work. The one that we are going to highlight here are process changes, water network, minimum water network, and holistic water minimization options. And then there will be use of impure water feed, outsourcing, and things like that, cost estimation involving the 3R, batch processes, simultaneous, and interplant water integration has been extensively done by so many people. They have contributed so much, and such great works has been highlighted. And this has been done along the line of graphical and insight-based approach or algebraic approach, as well as mathematical programming approach. We have done them as well. We realize that the part that we are going to highlight here is the most glaring gap that's available on the process changes, minimum water targeting, holistic water minimization, and we will highlight to you what we have done in terms of rigorous solution on mathematical programming very, very quickly on that one. So what we are trying to solve is a set of in industry or activities or even domestic and public facilities. You will find that you have various sources and demands, water sources and water demands. Water sources and water demands, we call them global water operations or activities. It is desired for us to design an optimal and holistic water network, to get the E for the economics, the cost, minimum net annual savings, considers all water management hierarchy, and payback period for retrofit using mathematical programming approach. This is what we have done before. Before we further go on, let me try to remind us that basically when we talk about water demand, it is water input into an activity, not necessarily a process. It can be a very simple household activity. We can talk about water source as water output from any types of activity, a process or an activity that a person does. Okay? So the methodology we're going through is to collect the water activities and then look at the possibilities, all possibilities to reuse, recycle, reduce water, eliminate water, all the possibilities, and then do mathematical formulation, and then do the regular computer-aided approach. This is what we have done, and what we do is to have a superstructure of network. Superstructure of network means that why not we try to find every possible solution to reuse water, from the source to the demand. So this is a superstructure of the network where you have sources, on the right-hand side on the green, and the demands on the yellow. B is the demands. And we have to take into account as water regeneration as well. Water regeneration and reuse, and the possibility of using water from the environment, outsourcing water. Okay? And then finally we come up with what we call as MINLP program. Because of the constraint is nonlinear, you have 6/10 costing factor that makes the equation nonlinear, then we have a nonlinear problem. Basically, what we are taking into account is the saving from fresh water, saving from wastewater. Remember the W3E nexus, saving from the chemicals, saving from the energy, and that will give us a holistic approach, holistic solution for water network. And then we take into account the cost functions, which is 6/10 cost function. This is nonlinear cost functions. And then we get the payback period to satisfy the last E, which is the economics. Because plant would not be too happy if you propose 100% saving, but it will take 20 years. So we have to toe the line what plant requires. For example, they say 2 years, then this is the client. We try to make sure that it will be within the period of 2 years payback. That is the plan, as the plan requires. So engineering water system holistically. Then we have this reduction elimination that is coupled with this previous formulation to take care that, of the elimination, reduction, and elimination and reduction solutions. So issues about this modeling. We have done it, but there are issues about the modeling, and these are the feedback that industry gave to us because we don't understand too much about it. We lack interaction. We don't know what is going on when you give us this mathematical formulation. They told that to us. Basically, we provide the solutions, and we cannot manage the complex. It's too complex. We cannot do much about that. We cannot utilize that too much. Then do you have alternative? So that we will be able to understand and make decision together with you. So, because we are fully, we try to make sense of the water minimization methodology, and then we try again. First of all, let's go through the methodology that we have proposed using the modeling approach and try to make sense out of it. Limited water data extraction. This is basically, if you have, for example, a domestic water minimization activities, then you just try to list them down. What are the water data? For example, in the case of us, basically, we do for prayers, we do the ablution, we do bathing, and this is the concentration. And the demand process for ablution, bathing, washing car, and things like that has been listed there. The key parameters involve flow rate and mass load. The mass load can be BOD, COD, and so on, so forth. Okay? And then we go to the next step, which is superstructure. This was formed into modeling, but we can do a down-to-earth water minimization case. For example, we have the fresh water. We have many users of the fresh water. Now, in Malaysia in particular, we do not recycle them at all. What we do is try to use everything using fresh water. And we audit the water, for example, like that, yeah, in terms of liter and in terms of concentration. And finally, we generate a superstructure. What we call a superstructure is actually all possibilities to recycle and reuse water. Can you do that, basically? Yeah? Which are the best reuse matches? We want to know. How many blending options possible? The water ratios. How do we ensure contaminants do not affect the processes? Yeah? That is the second stage, superstructure, and then mathematical formulation. This is the tough part for us to convince industry. So what we do is stepwise approach. We decompose the problem into what we call targeting and design, break into manageable parts so that the industry can understand better. We basically draw the source diagram. Water sources we represent in terms of cumulative concentration and cumulative flow rate. Yep. Each of them, we draw them sequentially. Yeah, this is the sources and the cumulative sources, each of the sources. And then we also draw, in the same manner, the demands. And finally, what we can do, we look at all possibilities to recycle water. When there is overlap between the source and demand, it means that you can reuse that water source to satisfy to the water demand. And when there is no overlap, these are the minimum amount of water, fresh water that you have to use, minimum amount of fresh water, minimum amount of wastewater that you will generate. So this is just the targeting part, just to show us what is the benchmark usage, the minimum amount of water that we will use in terms of fresh water as well as wastewater. Better and greener ways not to use water, use less water, remember, yeah, to satisfy the W3E. Can we do something else to do the problem holistically? Yeah? So we want to know the best mix option, not to use and use less. Why not we try to directly reuse? We know the option of directly reuse. Whenever there is overlap between the red and the blue curve, it means that we can reuse water, basically subject to the contaminant concentration. Then we have wastewater generation and then freshwater generation. If you have overshoot of the source stream, this is what we call as the pinch, yeah? This is the pinch point. It means that that is the maximum that you can use water. The pinch is basically what is the maximum that you can use the water for, reuse the water. That is the pinch. That is the maximum. You cannot go further than that with the conditions. So above the pinch, you will see that you can have this, try to find out if you can reduce this overshoot of the source of water. Yeah? You can reduce this overshoot of the source of water. You can also think about how you lengthen, because you want to make sure that the blue part and the red part overlaps as much as possible. What you can do, look at the blue curve there. This is a demand, this is a source, and the source is much more than the demand. Why not try to lengthen the blue curve such that you will have more demand and you can recycle more water, yeah, for it. So, or you can reuse. If this is the amount of wastewater you generate, can you try to think about how we can take just this portion and try to treat it such that it can recycle to that portion so that you will have more overlap. Yep. So integrate with demand below the pinch, that will reduce the wastewater and reduce fresh water. If that is something that we can do, yeah, on the third level, regenerate, reuse, then we would be able to save more water. For example, this overshoot part is the source of wastewater. Treat it, find a regeneration approach that you can do, the most cost-effective, and satisfy, instead of fresh water, use the regenerated water. That way you do not have to treat all, you treat just the right amount and give it to the fresh water, replace the fresh water. So that way you can play around. And the industry is very happy about being able to understand the numbers and everything. So finally, you do the network design, not something that I want to go through now. And let's go through an industrial case study. Framework for cost-effective minimum water utilization network. Water sources, I disguised the names of the basically sources and demands. This is total cumulative water flow rate. And these are, remember, the water data, water activities in the industry that we have extracted. Implementing top priority wastewater minimization options. So this is the maximum water recovery. You can see the overlap. This is the wastewater target, the freshwater target. So our objective is to try to play around with the curves so that you can reduce the overshoot there and reduce the overshoot here. If you manage to reduce the overshoot there, it means the water sources will be reduced to the extent that you want to reduce them, to the extent that you subject them to W3E, including the economics, yeah? And if you manage to reduce that, you would be able to even go for zero discharge. Yeah? If the plant wants to go for zero discharge, cost effectively. Yep. So let's try to look at, this is the first overshoot that you have. Overshoot means there is no overlap between the demand, D, and the source. First overshoot, eliminate S6, for example. Try to eliminate S6. Yeah? Eliminate S6 by what? By, for example, source switching. Can you use, for example, fin fan cooler instead of water cooler? Example, it's not necessarily you apply that. So eliminate the use of S6, so you will see that from 99 point something, it reduced to 84.77 if you manage to do that. And then wastewater reduced by 14.5%. Next, consider increasing D3 because we want to have as much overlap between the demand as well as the source. So increase D3, demand 3, we may be able to try to increase them. But remember, subject to W3E. Yeah? If you manage to do that, you will reduce significantly that part of water source that is overshooting, and you will see that many of the source has been catered for by this new demand that's been increased. Demand in stream above the pinch increase, further reduction of 61.3%. Next, consider eliminating this overshoot of the demand. Because there is no source there, you use fresh water, try to think about reducing demand. So basically, and then you can also think about regenerating S5, for example, because there is still some overshoot. Yeah? And send to the process below the pinch, because the process demand water, and send to the process below the pinch. And finally, you will see that freshwater target becomes 21.1 to 2012. We are not saying that this is implementable, this is definitely what you want to do. No, not necessarily the case. But you have a tool to evaluate, that's what we're saying. If you want to evaluate it and industry want to use it, implement it, by all means implement it. If you cannot implement it, don't implement it. So we are not saying force anything down anybody's throat that you have to implement these things. So regen leads to reduction, and these are the potential. It's not necessarily implementable, but you have to go through the stages of evaluation and then implementation. So these are the series of stages that we have gone through, and network design and allocation, and finally, the final design. Okay? Before, this is maximum water recovery, the typical solution people use, reuse, and so on. We also want to know water-wise or dollar-wise. Yeah? We have also an approach where, for example, if we use reuse only, reuse plus eliminate, yeah, this is the investment, this is the annual savings. Yeah? And then if you use external outsourcing, for example, this is the curve. And if you add with regeneration, the curve becomes that one. You can decide immediately which particular option is the limiting part in terms of the cost effectiveness. Why? Because you know that basically if you try to reduce any of the gradient there, you would be able to reduce, for example, the total cost. Say, for example, the total cost now, investment versus annual saving, the payback period is going to be very high. Why? Because the external, the external water usage is the steepest gradient in terms of investment. What you need to do is just to try to cut the steepest gradient. How do you do that? The first strategy is to try to substitute, for example, if a tank uses stainless steel tank, or maybe steel tank, stainless steel, sometimes you use it because you really need to use it, but steel tank, for example, can we try to substitute it with cheaper types of material tanks? So M4 becomes lower, and it will be able to satisfy the investment that is required by processors. The second strategy is intensification. Still M4 is basically the highest gradient. What we want to do now is try to reduce the size of M4 such that it becomes smaller in terms of storage tank. Rainwater harvesting, for example, can you harvest a lot? If the plant says, no, we cannot spend payback period of 10 years, okay, we suggest you do half the tank size. Half the tank size means instead of the maximum rainwater harvesting, just half the rainwater harvesting, you will see that the external source becomes lower and it will meet, basically, the requirement of the plant. That's intensification. So that's what we did in what we call as systematic hierarchical approach for cost-effective minimum water network screening. Yeah, sharps, mouthful, but we put into sharps. There are limitations of the graphical approach. We tend to get excited about graphical approach, but there are many limitations, of course. First is multiple contaminants. We have done the industrial part, and what we do when you have multiple contaminants and you need to use the graphical approach, then you do the localized integration with similar types of processes. Similar type of processes, you will be able to recycle similar types of streams or wastewater, localized integration. But if you use site-wide integration, then you are going to suffer because you are not going to get the optimal because there are so many contaminants. Yeah? So localized integration, not necessarily guaranteed that you'll be able to do that, but this is one solution. It seems that cut and paste, but the other thing is basically reconciling, iterative approach. Iterative approach, if anybody is interested, we will show you how to do that. Iterative approach, contaminant by contaminant analysis. Oh, okay, this is the one. Localize, reconcile, and iterate with other contaminants. This is for graphical approach. But when we have been able to convince industry that this is a way to go, these are the solutions for us to adapt, then we back to the rigorous solutions, multiple contaminants. Because they understand it, they already understood it, and there's not a problem, because they are very much into the solution, then we go back to the multiple contaminants. Yeah? So these are some of the things that we have done, the optimal water network, sensitivity analysis using a mathematical approach, and public as well as commercial facilities. This is a commercial facilities. This is a mosque in UTM that we have done. Optimal water network design for Sultan Ismail Mosque in UTM. And these are the payback periods and results. If you are interested in them, I can go through. Highlights of other results. These are some of the highlights that we have done with industry. And the software that we do, just to show that for industry, they are able to appreciate the technique, but they do not want to do calculations or use Excel and so on and so forth, then we propose to them to use the software to assist them in making the decisions. In a nutshell, there are advantages and disadvantages of many techniques, as any other techniques have advantages and disadvantages. So basically, the multiple contaminant approach of mathematical modeling, they are power. They address complexity, but we lack insight, interaction that industry wants. So on the other hand, the graphical approach, they are interactive, give physical insights, easier to understand, and people to participate, but they are tedious sometimes, and only suitable for simpler systems, only applicable, sometimes applicable to single contaminant, but we can address the multiple contaminants in some cases. So basically, why do we need to engineer water sustainability, safeguard companies' license to operate? Basically, among the pains of industry is that they need to operate, they need to have license to operate. If they pollute, they won't have license to operate. This is the powerful regulation. They're always over the world. People have this regulation, and companies need to abide by them. It will reduce purchasing, treatment, and discharge costs, the second E. It will avoid production disruption, cost, economics. It will protect the environment, the third E. So W3E is there for us to abide by them. Okay? If I have time, I can show this, but if time is limited, yeah? Okay. But before that, I will just give the key take-home messages. Yeah, water shortage for one of the world's biggest risks. Engineer water sustainability using holistic water minimization and subject to the W3E. And apply the winning strategy of blending power with insights. Yeah? So there is no competition whatsoever for us. It is actually cooperation. Yeah? So I would like to acknowledge the cooperation and those who have contributed one way or another, and significantly the Center for Process Integration and Intensification from University of Pannonia, Ministry of Higher Education Malaysia, and a huge thank you for SDEWES, and congratulations to SDEWES, SDEWES in particular, with a team who has organized the 10th conference, who have a very big vision in mind to do something to make a difference to the world. Thank you very much, and if I have 2 minutes, I can show the video. Okay, thank you very much. Can I get help from the technical team, please? Just to show the video. It's in there. It's in there. Escape, and it was in there. Escape. Just to go back to the folder. Yes, the drama. Okay. That's for 2 minutes. Yes, sound.
Manan. Tender loving and harmony. I'll give you everything inside. If you would give me a try. This is time, a time for changes. Anybody's fool can see. This is a day for you and me. Anytime you are ready, I'm gonna run to you. Anytime it could happen, and make this dream come true. We can make a new life again. I'm living for you, can't you see? So take a chance on me. This is time, a time for changes. Anybody's fool can see. This is a day for you and me. Anytime you are ready, I'm gonna run to you. Anytime it could happen, and make this dream come true. No thunder and lightning will keep me away. Any moment you call me, I'll be on my way.
Bil sampailah. Alamak, tingginya.
Itulah kau, aku cakap dah. Kan duit kau dah keluar macam air. Lain kali guna air tu jimat-jimat dah sikit.
Habis gaji aku bulan ni.
So I hope you notice that the W3E is in practice there. Come on. Thank you very much for your attention.
Thank you very much. You've got perfect timing, exactly 45, so we've got 15 minutes for discussion, and I believe it will be some. Okay, this is the first one.
Myself, Sharma from Italy. So thank you very much for the very good lecture. Now my point is concerning when you touch the economic aspects, that in the industrial you can reduce the cost. So in the first SD where you mentioned that by using cheap material for the storage tank, the cost can be reduced. But my point is that in the European community we have the well-defined European directives for the storage tank to be used for in the industrial sectors, where it is very well defined that which type of material to be used and what are the different characteristics of the material to be used for the storage tank. So how will you tackle this problem of using the cheap material for the storage tank? The first question. The second question is, according to your experience, vast experience, I would like to know which is the best available technology that can be used at the industrial level for the wastewater treatment. Thank you.
The first question is abide by the regulation. Simple, abide by the regulation. The first question, just to answer the first question. We are giving you examples. If it should not conflict with the regulation, the example should not conflict with the regulation. If you have regulation for materials here, then abide by the regulation. And then wastewater treatment, or I'm not suggesting the wastewater treatment, you remember. I'm suggesting to go through the holistic approach. And if you have gone through the successive level of approaches and you find it is needed for wastewater treatment, I'm not expert for wastewater treatment. This is a public confession, so basically you may be more expert than me. But my proposal is not to assess all the wastewater treatment, assess successive level of the hierarchy. Thank you very much.
Thank you for excellent lecture, and thank you very much for bringing the issue of water energy nexus, which is very interesting to me. My question is the time. We know that electricity is very expensive to store, while water is quite cheap to store. If we have excess of energy, of electricity at some times, can we use water side in order to store energy in that way, by using energy only when we have cheaper energy available? This is a question that arises from the thing that is happening now in many countries, is that we are moving to intermittent renewables, and that water is an excellent sector in which we can sometimes use very cheap energy, and sometimes the energy is very expensive.
Sure. I think you have answered the questions. Basically, the answer is yes. Why? Because you can store water. When you can store water, this is a significant advantage for you to use energy at the right time, at the cheapest time possible for you to transport water or do whatever you need to water. But then again, in industry, if it's a batch process, you cannot afford to lose the batch, for example. So this is a constraint that you have to handle or tackle. If there is no such constraint, then by all means, manipulate the time or take advantage of the time to use cheaper energy. That's, I think, the simple answer I can use. They are subject to various constraints, but yeah, I agree with you, yes. You can store and take advantage of the cheaper energy. Thank you very much.
Yes, please.
Thank you. Thank you for the presentation. Vince Abachovner, PS Energy. Is there any study cases for well, like oil and gas well and drilling in general of this model?
I have not done any study cases on that, but I think it's applicable. It will be applicable. The successive levels of hierarchy will be applicable case by case. I do not understand the technology of the well. But if we know the process, we know the description of the process, the nature of the process, we'll be able to apply the thing.
Thank you.
Yeah.
Okay. Another? Yes, at the rear.
Hi, Simone Levering from South Africa. Just wondering, have you applied it to any mining processes before? Especially the problem with mining in South Africa is that we've got inputs from very polluted water sources and from historical mining over 100 years, and now the new mines have to be treating that water. So there's a very high cost in the water treatment there. So just wondering if you've looked at that at all.
I've not gone through, we have not worked with mining industry so far, but as the case of well industry, as long as we know the processes, yeah, as long as we understand the process, have the process description, we should be able to cater for the case of mining industry as well. I understand that mining industry may be using a significant amount of water and the water are quite dirty. There may be a lot of cases about partially regenerating or partial treatment of the water for you to reuse the water, yeah, back. And in the case of mining industry, I would suspect, yeah, I don't know, but I would suspect that it can also, the demands can also accept spent water, not necessarily fresh water. So there is tremendous potential that I would suspect for us to do this technique for mining industry. That's the best I can suggest, yes.
Okay.
Sorry, just a quick follow-up.
Okay.
Just about the mining processes then close after, say, the next 50 years. After that, the mining houses can't bear the costs anymore, and then the costs have to be brought over onto the public.
Okay.
And does your, I don't know, model take into account when you don't anymore have that big capital being put in to, you know, reuse and manage the water resources?
Yeah, one of the factors, parameters that we took into account, I'm glad that I showed the modeling part. One of the parameters that we took into account is the capital cost. And the capital cost, the size of the treatment system, so it should be able to take it into account. Thank you very much.
Okay, next one.
Thank you. Thank you for the very nice presentation and the very nice video. I like the presentation very much. My name is Mohammed Shiab from Qatar Foundation. My question is, you know, your focus in your job is about reducing the amounts of wastewater as much as you can.
And fresh
so,
water as well.
Yes, and fresh water, yeah. So it is about reducing waste quantities, you know, of used water, let's say, fresh or wastewater. But what about, did you take into consideration the end pipe product, the wastewater, the quantities, because the quality, because you are mixing different sources of wastewater from different sources, as you mentioned in your presentation. What about, you know, did you think about how we will treat, you know, this mixture, strange mixture of wastewater from different sources? Thank you.
I can say what you're saying and what we do is quite contrary. It's quite different. What we do here is basically not to mix. And you were saying we are mixing. No, we are not mixing it. In fact, what we're doing is to avoid mixing, yeah, until we get, for example, a very easy example is the municipal treatment system, municipal sewage treatment system. What you do is mix the black water with gray water and yellow water, for example. They mix and then treat back. But what we're suggesting is partially treat the water from the sources of the water and then recycle it back. So the cost of the treatment or partial treatment, it should be less, much less than if you were to mix them, because now you have multiple contaminants, significant amount of yellow contaminants, gray contaminants, black contaminants, and then you have to treat it. Even fresh water that you were brushing your teeth and let it go down the drain, you have to treat it like black water if you were to mix them. We are not suggesting that. We are suggesting if it's white water, then don't treat it, just reuse, kill the bacteria, recycle. If it's black water, treat as black water. There will be significant amount of black water recycled to the part just needed. For example, if you treat black water, you can send to agriculture. They need the compost, they need the bacteria there to grow, for example, but you have to study whether the bacteria is suitable or not. So you do not have to treat that much. So you send to agriculture, for example. So you treat it, segregated treatment is not just mixing treatment. So the technique is suggesting that you do the better option and go through the successive with treatment as the last thing in mind. Abide by the regulation. Do not violate the regulation, and then basically treat it as you need to treat. Not mix them. Thank you.
Okay. Anybody else? Yes.
Thank you for a wonderful presentation. My question is not about the specific industry, but university campuses.
Okay.
On university campuses, for example, ones that can have more landscaping, more water-intense laboratories, or even district networks can have more water usage than others. But what would be your suggestions to reduce? And second question, I know that University of Malaysia has the Green University Index. How could such water minimization techniques be scored in such an index?
So, first of all, we presented, even though we presented very, very quickly about the MOS water minimization in UTM, I did not know you were there when I presented. There is a case study, and we have published a few papers on that. We can share it with you. So what you have done, we also might have done, but using this approach of holistic water minimization, taking into account of not to use water, reduce water, recycle, reuse and water, and going through the successive and finding the cost-effective means that is required by the university. And the sustainability index, I'm not the best person to comment on that one because there is a sustainability group, but what they are doing essentially, water index and energy index, basically they have a factor that is used to normalize this index and formulate a composite index that has one parameter, that is combined to give one indicator that is influenced by various parameters. That's as best as I can do because I'm not the expert in this area. Thank you.
Okay. Got chance for the last question. Yep. At the very rear. Elvis.
My name is Elvis Ahmetovic. I'm coming from University Tuzla. Thank you very much for really nice attention. Just please, could you give us your opinion about possible future directions in the area of water and energy integration?
Two possible areas that we are actually working and have not get a satisfactory solution on is actually, we are actually working on them, is actually water and wastewater integration. Water and wastewater, the whole supply chain of water, I show you the value chain of water, integrating the supply and demand side of the water, and then finding the holistic water minimization approach, or applying the holistic water minimization approach across the supply and demand side. Now we are catering only for the demand side. It will be more complicated because the wastewater network system is a bit more complicated to handle. That's one thing. The other thing is simultaneous energy and water. Tackling the W3E in total. W3E in total, water, energy, simultaneous water, energy, and environment nexus as well as the economy together into one model and graphical approach. Graphical approach is more challenging. I'm not sure at the moment that we can handle that one.
Okay, sorry, we can talk, I believe, still a couple of minutes, but we need to get the floor to the next session. And I would like to thank Professor Manan and present him the appreciation for the magnificent plenary lecture. Thank you very much. And it's a perfect time because the next chair lady is just entering. Oh, she deserted us. Yes, she's just coming, and I would like to ask her to take the chair because we have no break. So let's to continue.
Thank you, Yuri. I think that we can. Yes, we need maybe 2 minutes to arrange technical issues and to prepare for this session.